Now that we have designed the 2x8 beam to resist the normal stress, we now must check it for shear. This is an analysis, again, actual being less than or equal to the allowable, and our equation for shear stress, VQ over IT, must be less than the yield shear stress divided by the factor of safety. In order to solve this problem, we obviously need to know Q. The equation for Q is y bar prime times A prime, where A prime is the outward area. Our plane of interest is along the neutral axis, since we know the maximum shear occurs at that point. So our outward area is this. And our y bar prime is the distance from the centroid of the section to the centroid of the outward area. That on our diagram. So our y bar prime in this case is 1/2 of 3.75, or half of the height, inches. And our outward area is 1 5/8 inches times 3.75 inches, for a total first moment of the outward area of 11.42 inches cubed. From our shear and moment diagram, we know that the maximum shear force, including the beam weight, is 745 pounds, multiplied by our value for the first moment of outward area, 11.42 cubic inches that we just calculated, divided by the moment of inertia of the section, 57.1 inches to the fourth, which can be found in table A-15, and the thickness of the cross-section at our plane of interest is 1 5/8 inches. So the question is that less than or equal to 1100 psi, the shear strength of this wood, divided by the factor of safety of 3.0. When we calculate this, we find that 91.7 psi is the actual shear stress, which is less than the allowable 367 psi. So this design is okay for shear. Next, we'll be moving along to checking the deflection of the beam. And in order to check for deflections, we need to take a look at the loads again on the beam. Going back to our original loads, we know that the distributed load is 198.7 pounds per feet, and we have no other loads on this structure, so the maximum shear stress, the maximum deflection is found just based on case 7 from table A-19, and our equation for that is negative 5 WL to the fourth divided by 384 EI. Substituting in our values, minus 5, 198.7 pounds per foot. Knowing that we expect our deflection to be in inches, we'll convert the feet to inches. And our length, 7.5 feet, we'll convert that to inches as well. And that term is raised to the fourth power. That's the numerator. The denominator, 384. Modulus of elasticity for this material is 1.29 times 10 to the 6th psi, and our moment of inertia for this cross-section, as we found in table A-15, is 57.1 inches to the fourth. When we solve that equation, or evaluate that expression, we find that it is negative 1.192 inches, rewriting that as 0.192 inches down at midspan.